Yeah, so welcome everyone to the fourth straight season of the Isogeny Club. Today it's my great pleasure to introduce Simon-Philipp Merz, who's a PhD from Royal Holloway and currently a postdoc at the ETH Zurich. Yeah, and he will present SCALLOP. So yeah, please take it away.
Thanks, Jonathan. Yeah, hi everyone, and thanks for showing up. Welcome to this event. This is about a somewhat scalable effective group action from isogenies called SCALLOP, and there was a joint project with Luca, Boris, Peter, Antonin, Lorenz, and Benjamin. I think I even see some in the audience here. So the goal is to first set the stage why we care about these effective group actions, also for the security levels that we can instantiate with SCALLOP, then describe some of our design rationale in how we instantiate the scheme for specific parameters, and then give a high-level overview of how it works, some results about our implementation, and then open problems. Feel free to interrupt me for clarification questions. But otherwise, you can also ask questions in the end. So the bigger theme is cryptographic group actions. So what are these group actions? Well, it's a function that of a group that acts on a set such that the identity sends elements to themselves, and this group action behaves well under multiplication in the group. So the product acting on a set element is the same as acting consecutively by the two factors of the product. Now, to make these group actions interesting from a cryptographic point of view, there are two problems called the vectorization problem and the parallelization problem. The vectorization problem is you're given two elements in the set. You want to find a group element that sends one to the other. It's kind of like the discrete log analog of a group. And the parallelization problem is you're given three set elements, one, well, just X, then some group element acting on X, and some other group element acting on X, and you want to find what is the product of these two group elements acting on X. That's kind of the Diffie-Hellman analog in the group. So typically, the group actions we care about have some additional properties. For example, they might be free or transitive. So in this case, this means there exists precisely one element that maps any two set elements onto each other. Now, this will probably not be so new for many of you, but what is an effective group action? This was first introduced by Luca De Feo, Navid Alamati, Shika Patranavis, and I think Hart Montgomery, yes. So for a group action to be interesting, we might ask for additional properties. So what they called an effective group action is one that comes together with algorithms that are efficient. Efficient means here probabilistic polynomial time. Algorithms for certain operations, namely membership testing, equality testing, and sampling in your group, as well as computing the group operation and inversion in the group efficiently. And you want to have like membership testing and unique representation in your set X. But the main point of an effective group action is maybe even that you can evaluate it everywhere. Like any group element can act on any set element, and you can efficiently evaluate that. Now, this goes wrong for CSIDH. Most of you should be familiar, or I think I pitch it so that I assume that most of you are familiar with CSIDH. There, you cannot evaluate the group action efficiently for all the group elements on all the set elements because CSIDH is what's called a restricted effective group action. So this is also, there's also a framework for that by Alamati et al. So what does the restricted effective group action mean? You can actually only evaluate the group action on certain representations of elements in the group. So certain group elements, to be more precise, that span your group G, for which you can evaluate the group action efficiently. And then if you do that consecutively, you can evaluate it on the products of these group elements, as long as the exponents are not so large. And this is precisely what CSIDH does. And we know CSIDH is great. CSIDH, you can build non-active key exchange. It's fairly efficient, it's fast. So why would we care about the difference between a restricted and an effective group action? I guess that's the question. So I brought like one example why we might care. Namely, there's these identification protocols that you can build very straightforwardly from a group action. So you have a group action G acting on a set X, and you want to prove knowledge of one secret group element corresponding to a public key, which is like two set elements in this case. Like, yeah, two set elements. My notation suggests I'm thinking of curves here. So E0 and E1. E1 is the image of S, the secret acting on E0. And the way a prover can prove knowledge of the secret without revealing it is by first committing to another set element, which is just randomly sampling a group element, acting on the E0 element and sending it over to the challenger. The challenger will send back a bit challenge, so 0 or 1, upon which the prover reveals the secret element to the bit, so 0 or 1, times the inverse of the random element sampled in the group. So that the product of that sends it back to the challenger, which can check or which can evaluate the group action of this group element on the challenge set element. And if it is then equal to EB, where B is the challenge bit, so E0 or E1, then it accepts it. And this is easy to show that it is zero knowledge, because the group element R perfectly hides the secret S, as long as we can evaluate the group action on any group element. Now, this is nice because it allows us to turn this scheme into a signature just by replacing the challenge by like a hash of a message. So this is like the Fiat-Shamir transform in short. And so that way we have like a very simple, efficient signature scheme. Unfortunately, though, if we use a restricted group action, then this falls apart quite quickly. So the zero knowledge breaks. It's quite easy to see that if you have a random element only sampled essentially in a box, thinking of these exponents of your fixed group elements, and then the secret, then certain elements will fall outside the box, which will leak information about the secret. I don't want to go too much into detail. There is ways of working around this. This was done in CSIDH. You need basically an even larger way of abundantly representing elements, and then you reject all those ones that might leak some knowledge about might leak some information about the secret. So this is rejection sampling, but while this allows you to build signatures, it will lead to a considerable increase in parameters, and it's quite slow. So it would be nicer to have effective group actions for signatures, for example. Now, this raises the question whether we can transform a restricted group action into an effective group action. So for now, let's assume that the group acting is cyclic. In fact, for the groups we think of in isogeny-based crypto group actions, this tends to be the case conjecturally. And well, it might be cyclic or something close to cyclic. And then A way to transform a restricted group action to an effective one is to first start by determining the structure of the acting group. So what we can do, or what we should do, is to pre-compute the cardinality of the acting group and compute what we call the lattice of relations. So the lattice of relations are those exponents of your group elements for which you can evaluate the group action such that the product of the group elements to these exponents act trivially on X. So they are kind of equivalence relations of your group action. And then you can compute the reduced basis of this lattice of relation. That may allow you to solve the closest vector problem here, CDP, efficiently. Now, if you can do such a group pre-computation, so this just has to be feasible, it just has to be done once, it doesn't have to be particularly efficient, but it has to be doable. Then if you want to evaluate L1 to the E for an arbitrary integer E, recall that L to the E is a generator of your group. So L1 to the E means all the elements in the group. If you want to evaluate the group action for such an L1 to the E, then you can just solve the approximate closest vector problem, or the closest vector problem of this vector E followed by zeros in your lattice of relations, which will allow you to give a different representation of your group element in terms of like a product of with relatively small exponent. So there you're back in the setting of group actions that you know how to evaluate, and then you evaluate it with your restricted group action. So this is a nice idea, but depending on the group, the pre-computation might be quite expensive and become eventually computationally infeasible. However, this was precisely the strategy chosen by CSIDH, the CSIDH signature scheme. So CSIDH is a signature scheme that uses this Fiat-Shamir type signatures that I kind of summarized earlier, based on the CSI-512 group action, where the lattice of relations is first computed using some sort of index calculus approach, and then in the process you get kind of as a byproduct the class number, so the cardinality of the acting group. Now this is the smallest CSIDH parameter set, CSI-512, and to compute the class group there, this CSIDH needed to do a like world record class group computation to obtain the lattice of relations. This computation of the class group scale, well, is a sub-exponential function in the discriminant of your, or essentially in the P here, so the 512 or then 1024 for larger parameters. So this will not scale to parameters much larger. And yeah, at least with currently known algorithms, that seems to be infeasible to build an efficient signature from like larger CSIDH parameters. So this was just to set the stage and why we were thinking about introducing a new group action that might solve the scaling issues of CSIDH, at least to some extent. We'll get back to that. And yeah, it raised the question for which cryptographic group actions we might be able to compute the structure of the acting group more easily. Then we looked at one observation. So if you have an imaginary quadratic order and you want to compute its class number, so that's the number of elements of this class group, then you can do it if the imaginary quadratic order is of a specific form. So if it's of the form an integer plus some f times another imaginary quadratic order, O0, such that you know the class number of O0 and the factorization of f, then there's a simple formula here at the bottom of the slide how you compute it. You can also just ignore the last fraction for now, but it's essentially just, you need to know f, and you need to evaluate one Legendre symbol, and that's efficient as long as you know the factorization of f. Was there a question? Sorry, yeah, Tanya is right. So the CSIDH signature scheme, I mean, it doesn't scale with a class group computation on classical computers, but indeed, if you had a quantum computer to do the pre-computation, then we can instantiate also larger CSIDH signatures. So just from CSIDH. Should have said that. Yeah, thanks. Now, with this observation, the natural question is how can we build like maybe a class group action that uses these different imaginary quadratic orders where we might compute the class group structure more easily, which gets us to the topic of oriented elliptic curves. I think there were some talks in a previous season, but let's just recall the definition for now. This was first like introduced as a framework by Leonardo Collo and David Cole. So you have like an imaginary quadratic order, and then we say we have an orientation. Well, it's an orientation if you have a homomorphism that embeds the some imaginary quadratic field in your endomorphism algebra. And for this talk, we actually only care about orientations by an imaginary quadratic order. Also only what's called primitive ones in the literature, but I might just drop this primitive every now and then. That means this homomorphism embeds this imaginary quadratic order directly into the endomorphism ring of the curve, and it's the largest such imaginary quadratic order that gets embedded. And then we call the pair of the curve together with this ring homomorphism an oriented curve. Yeah, so you can just think of it as a function that embeds your imaginary quadratic order into the endomorphism ring. In SCALLOP, there's a question of how you represent your orientation. So you can do this by essentially mapping a generator, for example, or the generators of your imaginary quadratic order onto certain endomorphisms. And yeah, the endomorphisms will just, again, represent by what we call kernel representation, which is kind of typical in isogeny-based cryptography. You have an endomorphism, you just give its kernel. What's also quite standard by now is that you can represent endomorphisms not just by one kernel, but actually an endomorphism is kind of well, it's a cycle in your isogeny graph, so you can also represent it by two kernels that meet somewhere in the middle. And that's how we represent it as well. Now, why do I talk about oriented curves? What do they have to do with group actions? Well, if you have a set of these primitively O-oriented curves up to isomorphism and Galois conjugacy, then it is well known that that invertible ideals of O are acting on the set of O-oriented curves, whereby the principal ideals act trivially. So if you think of all invertible ideals of O divided out by the principal ideals, then this is the class group, which gives us like a class group action on the set of O-oriented curves. This was first, I guess, stated in this OSIDH paper by Collo and Kohel, but then later it was also proven by Onuki in 2021 that this is indeed a group action that is free and transitive. So this is a group action that we may want to work with. Now, this is all quite abstract. Let's look at how we actually, well, let's look at one example. One example is CSIDH. CSIDH is the orientation of Z by the order Z square root of minus P, where the generator square root of minus P is mapped to the Frobenius endomorphism of FP curves. Now, in general, how do we compute with these group actions using isogenies? Well, if you have an ideal in your imaginary quadratic order and you have an elliptic curve with O orientation, you look at, well, you look at all those generators of your ideal, and you map them through your orientation into your endomorphism ring. So they all have a kernel, you can intersect them, and this intersection of the different kernels gives you a subgroup of your curve B. Now this subgroup will have size the norm of the ideal, and it behaves nicely. And taking this subgroup as a kernel of an isogeny, you get to a different curve on which you can define again an orientation, kind of using the sometimes called the lollipop endomorphism or Waterhouse twist. So essentially by walking back the isogeny you just computed, taking the endomorphism on the curve you started with, walking forward again through the isogeny, and then dividing out the norm of the ideal. So this defines an isogeny action, and if you're worried that, oh, this ideal might be quite big, so this intersection is over many elements, well, it's sufficient to just consider this intersection over the generators of your ideal. So this is also what's actually done in CSIDH. So let's look at how we represent or compute with different orientations in CSIDH. In CSIDH, if you have an ideal that, well, of some norm Li, say, then we know that the isogeny that we want to compute to get from one curve to another is stabilized by the Frobenius endomorphism that corresponds to the square root of minus p. And to compute this group action, you actually just look at the Li torsion, you evaluate the Frobenius endomorphism on it, and this will give you like two eigenspaces. Each eigenspace defines like the direction to walk left or right, a horizontal isogeny on your like isogeny volcano. So you might be familiar with this part, but this generalizes more, well, generalizes. In more general, you can just look at an ideal in your imaginary quadratic order, and it acts again through an isogeny of degree the norm of this ideal, whose kernel is stabilized under an endomorphism that corresponds to the generator of this imaginary quadratic order. And now you can do the same thing as in the CSIDH case. Instead of looking at the eigenspaces of the Frobenius endomorphism, you can look at the eigenspaces of this endomorphism W or omega that acts on your Li torsion. And then again, you can walk left or right. What's the difference is that the orientation, so this iota from the previous slides, you always get kind of for free in CSIDH because it's always the Frobenius endomorphism. Whereas if you work more general with oriented elliptic curves, you have to always explicitly represent it somehow to know which endomorphism you're talking about and how to port it forward and backward. So there's some additional work involved. So let's just, I talked about a whole bunch of things, oriented curves, group actions. Let's just take a step back, what we actually wanted or what I've mentioned so far. So we wanted some group action for which we can compute the structure of the acting group so that we have an effective group action later, because we have a lattice of relation in which we can reduce the action and we can evaluate it everywhere. For that, we knew that for certain cases we can evaluate the class number at least, namely if we know the cardinality of some class group of some O0, and O is of the form Z plus some F, and O0 for which for which we know the factorization of the integer f. So this will give us the class number, so the cardinality of the class group of O, essentially for free. But then to compute the lattice of relations in this class group, we may still want this class number to be smooth enough. At least that's, I mean, I guess it's up for discussion whether this is necessary, but it's certainly sufficient. If it's smooth enough, then you can compute the lattice of relations just by solving some discrete log problems in this sufficiently smooth group, and therefore get the relations between your various ideals that act. Now, to then represent and compute with these origin-oriented curves, we further wanted to be able to represent the generator of our imaginary quadratic order. So we need some generator, I called it alpha, of this O that is of sufficiently smooth norm, so we can actually evaluate it later and determine its eigenspaces and so on. And so that we can actually write it down nicely over our base field. But I guess that depends on how we choose the characteristic. And all of this done, we still need to find a starting curve. So in CSIDH, I guess any FP supersingular curve will do. But here you have to find some O-oriented starting curve where you can start with this group action. And this is not a priori an easy problem, because even deciding whether some supersingular elliptic curve has a certain orientation is difficult. So how did we solve these problems, or how did we actually instantiate the group action that we can work with? Well, the name is SCALLOP, which stands for Scalable Isogeny Action Based on Oriented Supersingular Curves with Prime Conductor. That it's a maritime theme is, of course, completely coincidental. We solved it by taking as O0 the Gaussian integers. For those, we know that the class group is trivial and the class number is 1. So in particular, we know it. Then we generated candidates for this imaginary quadratic order O with smooth generator. So we kind of turn it around. And then given such a smooth generator, we tested whether the conductor is prime. That can be done quite efficiently. And if it's prime, we know it's factorization because, well, it's trivial. So we avoid factoring f in some sense. And then the last point on the wish list for the pre-computation was that we wanted the class number to be reasonably smooth. Well, given f and the class number of O0, we can compute the class number of O. And then, well, we had to test whether it's smooth enough. But I'll get back to this. Now, the second point was, again, quite high level. How do we sample a smooth generator until these certain conditions are satisfied? Well, we just took the smallest n-split primes in the Gaussian integers, which we had fixed. So say 5, for example, or 13, and so on. And we take the ideals that lie over 5. So for example, 2 plus I or 2 minus I. We take their squares of these generators, or just themselves, and just randomly sample signs. So you take 2 plus I squared times 3 minus 2i, for example, and so on, which gives you an integer that generates an imaginary quadratic order. By construction, it will be smooth. Namely, it will be of smooth norm L1 squared times L2, where L1 is the set of primes for which we took the squares, and L2 is the primes where we just took our 1 or minus 1, and for squares minus 2. And then you get some Gaussian integer as an output of this, where you just look at the coefficient of the imaginary part, and you can test whether it's smooth. You compute the class number as previously outlined for free, and you test the smoothness using just ECM factoring with a board. So just to give you a rough idea for the CSIDH-512 equivalent, we actually got a class number that is 2 to the 35 smooth, which is pretty smooth. So you can just throw away most of the class numbers you sample. We have so many that we can search through that you can just throw everything away where the coefficient of the imaginary quadratic part is not, the imaginary part is not prime, and then test its smoothness and also quickly abort if it doesn't lead to anything, because for 2 to 35, it's like pretty fast. And for the larger security parameters, we still had like 2 to the 70 smoothness. So it's still quite all right to test the smoothness here. However, you see that if we want larger security levels, somehow the class number will get gradually less smooth, and there's kind of a random process involved. We would roughly expect to have a sub-exponential search to get a sub-exponentially smooth class number. Now, if you're familiar with like class group computations, then you will say, oh, this is the same complexity as computing a general class group as was done in CSIDH, but the constant just seems to be much smaller, which is why it was still feasible. But eventually, asymptotically, we will run into similar problems. There was a question. Yeah, the second L in SCALLOP is a typo. So now, one additional thing that we haven't talked about at all is the characteristic of the prime field you work over. In CSIDH, you take it as like the product of the ideals you act with, plus minus 1, I think, maybe with a small cofactor. And the same works actually here. So first of all, we again want our horizontal isogenies to be defined over a small field extension. So this is the same as in CSIDH, and also the endomorphism, which we also sample, or which has a degree, a power also of these primes. We also want it to be defined over a small field extension, and then efficiently compute with it. So this is quite similar. Of course, we also have to take P large enough to prevent generic attacks that compute the endomorphism ring, but this is already, for our parameters, already guaranteed anyways. And then to compute the lattice of relation, we solve the instances of the discrete log problem, which is not an issue as long as we sampled a smooth enough class number. Again, back the scaling issue from the previous slide. And then we reduce this basis using BKZ, just as is done as CSIDH. So if you're, again, familiar with maybe some lattice problems, you will see, oh, lattice reduction, well, that's a hard problem. And in fact, asymptotically, it's also is exponentially hard. But the lattices we deal with here are of dimension as many L's as you have to do the action. And yeah, I think it's 65 or something in our case for the larger parameter sets. And there's even some room upward for larger parameter sets where lattice reduction would still be quite efficient. But yes, asymptotically, we might run into issues again within the lattice reduction part. And then finally, there was this open question of generating a starting curve with a certain orientation. So let's look at this problem a little bit more. So you have E0. E0 is the O0 oriented curve. And say you know some endomorphism of the correct norm, where alpha is the generator of your O imaginary quadratic order, and you want to find an primitively O-oriented curve E prime, and the endomorphism that kind of realizes this orientation. So the image of a generator of this imaginary quadratic order. And you can actually get from E0 to E prime by almost every isogeny of degree F. So any E prime would do. So E prime is just any of the codomains of a degree F isogeny, except for like two exceptions. So the maybe naive idea would be, oh, you're given a field, you're given the curves, you're given the order. You have already an omega 0 endomorphism on E0. You just push it through the phi isogeny of degree F, and then you get some endomorphism on some curve E prime. Unfortunately, you can't do that because you can't do that using the loose formula just by evaluating it, because F will be a large prime. So F is roughly the size 2 to the 2 times your security level. So for 128-bit security, this is a 256-bit prime. Also, square root values is not going to help you there. So you have to be slightly smarter. But we're lucky because the O0 we chose is what's called a special extremal order. Like for definition, I just refer to the KLPT paper, but the upshot is that for these special extremal orders, you can find some element in your order of norm M efficiently as soon as M is larger than your field characteristic P. So this gives us a game plan. Like, can we just find, say, or can we just find the alpha in or some endomorphism this way? Well, not quite, because well, F is a bit smaller than this field characteristic, so it's not far off, but there's still a slight gap, so we can't apply this result of the special extremal orders yet. But what we can do is we choose just another small prime L0 that's co-prime to our endomorphism of degree L1 squared L2. So it has to be co-prime to L1 L2. And we take a small power of this L0 to the H, such that this power is larger than P over F. Now, what does that mean? Well, that means L0 to the H times F is larger than P. So in particular, we can find an ideal or an element in the O0 imaginary quadratic order of norm F L0 to the H. And this will correspond to some endomorphism phi psi, that's the one in red, of degree F times L0 to the H. Now, how do we get, how does that help us? Well, for endomorphisms of non-smooth degree, we actually know how to evaluate them or how to push kernels through them. There's two references actually. So there's this one, which is some joint work with Boris, Peter, and Jan Botti. And then I think Antonin had a similar paper, the one at AsiaCrypt last year or 2 years ago, which independently also came up with this algorithm. Anyways, using this algorithm, you can push the kernel of your omega 0 on E0 through the endomorphism, which again gives you well, the kernel on E0. But this time, you know, you just have to push it through the shorter isogeny L0 to the H to get to E prime and to recover the omega prime on E prime. And we do this just by brute forcing. So L0 and H are small enough that we can just try the various candidates for psi and then test after pushing back the kernel onto this codomain, whether this indeed gives us an endomorphism of the correct norm and trace. So this is how we did it, and it's sufficiently efficient to run in practice. In fact, this was one of the fastest parts of instantiating the scheme. Now, the online phase I haven't talked much about, except for that it's very similar to CSIDH. Here on the right, you see the isogeny graph or the volcano we deal with in this particular case. In the center, there is the curve E0 that's oriented by the O0, so with a trivial class group action. So that's the crater is really just a peak in this case. And then the outer circle is all the O-oriented curves. That's the curves between which we walk horizontal isogenies in SCALLOP. Now, given one curve on the outside with the corresponding endomorphism that like realizes the orientation of this sufficiently smooth degree, represented by its kernel, we just look again at the isogenies with kernels stabilized by this endomorphism, and then walk essentially left and right on the outer circle. One issue here is that in each iteration of the group action, you have to explicitly compute a new representation of the endomorphism that realizes the orientation along this group action, and this explicit computation leads, for example, to a big slowdown compared to the CSI-FiSh, which comes with CSIDH's canonical orientation. But otherwise, it's kind of the same as in CSIDH, so I didn't want to go into more details necessarily. So let's just summarize a bit what the differences again are between CSIDH and SCALLOP. In CSIDH, you have one orientation by z square root of minus p. In fact, actually for a specific p, because it's based on CSIDH-512. Whereas in SCALLOP, it's like a more general framework of evaluating this oriented group action, as long as you have a imaginary quadratic order of the form some integer plus a large prime plus some O0 for which you know the class group. In CSIDH, you have the pre-computation, which is super expensive and actually only feasible for the smallest of the CSIDH parameters. Whereas in SCALLOP, you kind of get the class number for free, and then you need to do a bit of sieving until the class number is smooth enough to compute the lattice of relations. So asymptotically, not perfect, but much faster in practice. It runs in minutes on a single laptop compared to, say, the class group computation of CSIDH-512 for a similar security level. And yeah, in CSIDH, it took, I think, 52 core years to compute the class group. But then the evaluation of the group action with the implicit orientation in CSIDH is really fast, whereas we need to explicitly compute it and port it along our group action, which makes the online phase, unfortunately, while feasible, much slower. However, it's also still feasible even for larger security levels. We implemented this SCALLOP scheme with concrete parameters in C++, and it's available here under this link. For two of the instantiations, well, we have two concrete instantiations with parameters that should match the security of CSIDH-512 and CSIDH-1024. For those, the public keys are a bit larger than in CSIDH, but with 1,600 bits for SCALLOP 512 and 2,300 bits for SCALLOP 1024. It's still quite compact to other schemes. Unfortunately, though, the group action is quite slow, so that's where further work is needed. The SCALLOP 512 evaluation takes roughly 35 seconds and SCALLOP 1024 12 minutes. So the implementation shows more feasibility rather than that this group action is now already practical for applications. So let me summarize the main contribution. We have this framework to evaluate a new family of group actions on elliptic curves via isogenies. We have a concrete instantiation using, imaginary quadratic orders with large prime conductor inside an imaginary quadratic field of small discriminant. And then this, we can instantiate this or instantiate effective group actions with this for security levels that were previously out of reach to actually build anything effective group actions from. And that allows us to build, for example, signature schemes or also other cryptographic protocols that require to efficiently act by arbitrary group elements, also for larger security levels, more than CSIDH-512. But as you have heard multiple times in this presentation, there's a few open questions or a bit further work to do, mainly how to get this entire thing faster to make it more practical, and also interesting how to further resolve scaling issues of SCALLOP. There will still be a limit where we hit again our asymptotic issues with the sieving for smooth class numbers and also computing then the discrete logarithms of those, and then the computing a reduced lattice. So all of these, it would be interesting to find maybe additional ways to work around it if there is some. Well, thanks for your attention. More details is in the paper, and I would be very happy to get some questions.
Thank you very much for a great talk, Simon. Yeah, as usual, if there's any questions, please just unmute or write. Yeah, Tomoki already has a question. So do you want to read yourself, or do you want me to read for you, Simon?
Yeah, I just saw it. So there is I guess that the orientation of E has information on an isogeny between E and the curve of J invariant 1728. Yes, it does. But the isogeny is of order large prime and SCALLOP seems secure. Is it right? Yes. So like the issue is that you can't really move from between 1728 and some curve on that has a like F isogeny in between. So if this was not the case, then we're kind of in the same setting again as OSIDH. So if you have, say, if F wasn't a large prime, but instead say very smooth, then you could gradually walk your way along reducing the class action to like a smaller problem. So you can gradually break the problem into smaller bits. I don't think, or I don't know how to do it in this case. So yes, you're right. Are there other questions? Yeah, okay, why we choose the L0 as we do. So, what's that here? Yes. So, F is a very large prime. So, if you have a very large prime degree isogeny, you can't just evaluate it. Like, we don't have a way of evaluating it. What we do instead is we find and F is not large enough so that we can find an element in O0 essentially that is of norm F. However, if F was a bit larger than P, then we can do that because of this special property of O0. And what we use this L0 for is to increase F by a bit more so that it is larger than P, which then we can find efficiently an element in O0, so in the imaginary quadratic order attached to E0. That gives us an endomorphism, the red one, that runs through the curve, or one of the curves that we are interested in, for which we can't evaluate it directly, but it runs through one. And then, because the way back from this circle is essentially much shorter, we can brute force this part. I don't know whether that makes sense to you, or maybe the picture is slightly misleading, because you can think of this as the top isogeny is much, much longer than the bottom one. So maybe the arrow on the top should be longer. You also look a bit puzzled, Jonathan?
I'm just wondering a bit like why, if the path from E0 to the starting curve is so short, then it doesn't seem secure somehow. Like if that's the starting curve.
Well, I mean, in
but
CSIDH, you also know the starting curve. Like it doesn't give you any information necessarily between this curve and some other one. So this is just to get one of the points essentially on your, like on the volcano picture and on the outer circle. It doesn't really give you a connection to
no. Like CSIDH as well had, like, of course it's broken, but yeah. Indeed. Thanks.
Actually, I still had a question on this group action evaluation. For CSIDH, we have quite a lot of lower level techniques that speed it up a lot. Are there any that, like, do you know which ones also translate to SCALLOP, or are there some open problems there to translate them to SCALLOP to prove the performance?
I think that's interesting. I'm not sure. So I didn't do the fast implementation, so I'm not sure. I don't think we have employed any of these, say, radical isogeny, etc. techniques. Well, we didn't. I think one part was also that you can hope to speed it up by a factor 2, 5, 10, or whatever with these techniques, but that would still be fairly slow. I think it would be interesting, though. I don't think we have done any work in that direction yet. So that would be also an open problem.
Okay, cool. Yeah. Then there's still a question of Bruno in the chat.
You might have mentioned already, but is there any reason other for requiring the conductor to be prime other than ease of trying to factor it? Might one get some advantage of having composite conductor if it can be factored? That's a very good question. So the conductor, there is some security in there. So I did mention if the conductor was, for example, very smooth, then you're in the setting of kind of OSIDH. And I mean, even in the original paper, it was already mentioned that this is not secure with certain additional information. But there is a question whether it has to be a prime as long as it is large enough. So it could be the composite probably of some large-ish primes. Then you don't have this security vulnerability by moving back and forth, but it still has to have large enough factors that you cannot just say evaluate the isogeny. Exactly. So Pierre posted his paper, I guess, on attacking OSIDH. This is exactly the problem that of lifting along a smooth degree conductor, the problem up and down. But I mean, we choose it just as one prime for the ease of factoring. You might still choose it as a product of multiple fairly large primes, as long as well, they are large enough. I think large enough would be something like 2 to the security level, roughly, I think, but I would have to think a bit more about it. I mentioned that I said something like we can't find F directly or something like that. Maybe that doesn't make sense, but what I really meant earlier with why we can't use the special extremal order property was if we are not above a degree that is larger than P, then we don't know how to find elements efficiently in O0 of a specific norm, of that specific norm. We only know how to do it as soon as the norm is larger than P. That's just how it works. So we make an endomorphism with a factor F that is larger than P just by supplementing it with an additional factor L0 to the H. That's the idea.
All right. If there are no more further questions, or otherwise you have to unmute very quickly, then I think we
can.
Can
I unmute? Can I ask another question?
Sure.
Yeah.
Thanks. I was just really interested in asking about like because you briefly mentioned like the parameter sizes, and I was just wondering like because somehow like the vectorization problem and is dependent on the class group size, right? And then it's it reduces the endomorphism ring, which is only dependent on P. But does that mean that like in theory you could instantiate all of the scallop security levels over like 256-bit field? I mean of size 256-bit. Of course, I know that it's bigger in your implementation and stuff because you want all the torsion to be.
Yeah, exactly. Like I think we're already larger than to avoid the endomorphism ring attacks because we want to have our torsion points defined over a small extension field, and also the endomorphism that we kind of carry along to be defined over a small extension field. I'm not sure I get your question whether it would still be possible.
Like if it's secure, I guess. I mean, if you say you used like you didn't care about them being rational, like you were willing to use points over extension fields. If you could.
I think yes, I think so. I mean, maybe that would be interesting. I don't think any of the so we have a bunch of like attack vectors lined out in the paper that we discussed. I don't think we had anything that would like conflict directly with choosing a smaller P as long as it prevents us from computing endomorphism rings. If you don't care at all about efficiency and
Yeah. It's interesting because I just thought because then like I mean the parameters could potentially be small if you solve a bunch of other problems as well.
But isn't that the same in CSIDH?
So that's I agree, but then P and the discriminant of the order is of course very heavily linked together.
Okay, yeah. I think finding gamma of degree L to the H is more or less the representation integer step of KLPT, which only works if L to the H is larger than P. Yes, exactly. This is the represent integer algorithm. Maybe one comment. We don't want to represent L to the H, but we want to, exactly, L to the H times F. Otherwise, that would be a bit of an expensive brute force afterwards. Thanks.
All right. Thank you for my last minute question too.
Yeah, then you can also wrap up, Jonathan. That's your turn now.
Okay. Yeah, if there are no more further questions, I should ask myself really. But then let's thank Simon again. That was a fantastic talk. I enjoyed it a lot. And otherwise, we'll see you all next week. Then we have Ming-Jae, who's presenting Scallop HD. So maybe answering some of these interesting open questions that Simon raised in the end here, without spoiling anything, of course.
In 2 weeks.
In 2 weeks, sorry, not in 1 week, in 2 weeks, yes. So then have and as always, we'll hang around a few more minutes after the meeting if anyone wanna chat or raise some informal questions or whatever. Okay, well, thank you, Simon.
Thanks everyone for listening.